Right, so I will tell you about deep learning tools that we've developed in EXO-200 neutrinoless double beta decay experiment. I will mostly talk about stuff that is already published or already developed, a little bit at the end, new stuff, but most of the new stuff will be talked about by graduate students on EXO-200 that speak after me. Let me start by introducing the detector. So this is, again, a neutrinoless double beta decay search in liquid xenon. And we use time projection chamber, a single phase time projection chamber. In fact, it's constructed as a dual TPC. So there are two identical halves. This is one of the halves. And they share the cathode, so this mesh. And then there is another half just like that on top of this. And so when energy is being deposited in liquid xenon that fills this TPC, those electrons will drift towards one anode shown here or the other not shown here, and will get deposited on the wires. As well as the light flash that will be produced, it will be detected by the avalanche photodiodes. You could maybe see here the surround surfaces of the avalanche photodiodes. So we have something like 76 wires that collect the charge, and we have something like 148 avalanche photodiodes that collect the light. So for each event, we have these two information channels that allow us to measure energy and position from those distinct physical processes. And what else? Right, so we also have another set of wires that do not really collect the charge. They are transparent effectively, but they feel the induction as the charge cloud passes through them. And that gives us the complementary position direction. So from two sets of wires, you get effectively your XY position, and from the time delay between the light flash and the appearance of the charge, you get your Z position. So we can reconstruct all three coordinates in principle. Now, if you look at the raw data that comes out from the detector like that, you can represent it one way of representing it effectively as a picture shown here. So on the x-axis, you see the time steps. That's the digitization of voltage on a channel. So either it's a wire channel that collects the charge or feels the induction of the charge, or the light collection channel that is APD. And it's what's light colored here is, of course, the amount of voltage, the magnitude of the signal you see at a particular time. So when the event happens and the energy is being deposited, first of all, you will see this instantaneous flash. You can see the all APDs effectively lighted up. And then the charge cloud, one or more of the charge clouds that are being created by the interaction, they will drift, so there will be a delay. And eventually they will deposit this charge on one or more charge collection wires. And here you can see several wires that are being lighted up at different types. So what that tells you is that in this particular event, there were probably several charge clouds created. And that is characteristic of gamma-like interaction. That is a background for neutrinoless double beta decay search. While if you have actual neutrinoless double beta decay or other beta type interaction, the charge cloud is very localized, and you will, in most cases, see just one or two neighboring wires being lit up. So that creates effectively different types of pictures that if you're able to categorize into those different topologies, you should be able to differentiate between your signal and backgrounds. So now, there was a comment that in a neutrinoless double beta decay experiment, as perhaps compared to dark matter experiments, the energies are high and the detector is not as large. So maybe if your deep learning application were able to do a good job, maybe it's not as surprising. I think it's maybe a valid point, but I think the more interesting question to ask is not how this detector performance compares to another detector performance. Different detectors have their own issues that they respective analysis have to address. I think the more important question is how the performance of your machine learning algorithm that you developed compares to the standard analysis or traditional reconstruction. So I'll be using this term traditional reconstruction or EXO-recon also to denote this set of algorithms that we've been using for a long time. And I will compare the deep learning algorithms to that metric. And the traditional approach that could be roughly summarized, kind of briefly summarized as a set of algorithmic boxes, and different experiments, of course, will have different particular boxes, but each of these boxes applies some well-known techniques from signal processing to these raw data. So most of the time, analyzers, they don't really deal with those actual raw data pictures that I showed you. They look at these high-level features already being extracted by those individual algorithms. Match filtering, denoising, clustering, whatever, right? And so that's what I mean by traditional reconstruction. So that box, that is not black box because you know exactly what's going on there. But I would say it's also not a white box. I would say it's maybe a gray box because there are some things there that maybe some built-in assumptions that you're not always aware of, or maybe even sometimes mistakes and imperfections that you not always find immediately. That also kind of blurs a little bit the picture and introduce additional potential systematics. Okay, so I'm not going to be talking about high-level analysis here, so I think we can skip this slide. So when we started the deep learning effort, the question that we wanted to ask, can we go back and circumvent that gray box of the traditional recon and extract those high-level features directly from the raw waveforms? And when I say raw waveforms, by the way, I want to be explicit. I'm being a little bit loose. There was some comment earlier in the workshop that, oh, we subtract the baseline from the waveform, so we're not dealing with raw waveforms. When I say raw waveforms, I do not mind making some simple algebraic, almost like manipulation, like subtracting baseline or maybe scaling individual wires by their corresponding relative gains. I still call it the raw waveforms. Important part for me is that I'm not doing I'm not applying any of these little algorithms contained in the traditional recon box to the waveforms when I give it to deep learning. And so the question, can the deep learning extract the high-level information directly from that? And I think we answer it, at least for our experiment, conclusively, as other people, of course, did in other domains. Another thing that was very important to us, because there was a lot of pushback against using the deep learning methods, is they are the ultimate black box. And it's not clear why it does what to do, is can we validate our results, not just on Monte Carlo, but on real detector data? And that's also that we did. And even then, there is still concerns about Monte Carlo and the potential bias that it can introduce. So we also looked at the ways to limit our exposure to Monte Carlo. And in fact, in the detectors like EXO-200, where you have two distinct channels, there is this great advantage that you can sometimes use one of the channels to provide the quote-unquote truth information to guide the training of the deep learning algorithm over another channel. So sometimes it's possible, and that was a nice advantage that we discovered. So the first application was to reconstruct the charge energy, so the energy estimator provided by those charge collection wires, and using convolutional neural network. And we trained it on the Monte Carlo of different calibration sources, and almost out of the box, we got the energy resolution that is slightly better than what we get with our traditional recon, with EXO-recon. Now, when we start looking and try to understand what exactly is happening, so you can see here the Monte Carlo reconstructed by the traditional recon called EXO and by our convolutional neural network. You can see the improvement, and it actually happens in the what we call shoulder of the full absorption peak, these are thorium calibration events. And when we start digging and trying to understand what exactly happened, and we realize that a deep neural network is doing a better job at disentangling a very intricate detector effect that, by the way, only happens at those large energies. There is a particular effect, a physical or detector effect that turns on roughly from 1 MeV and becomes really prominent at 2.5 MeV, which is our region of interest, where the charge cloud that gets deposited on a particular wire, it also can induce charge on a neighboring collection wires. And this create, excuse me, this creates actually, apologize. This creates a lot of trouble for our traditional reconstruction. And network actually learned to do that and to disentangle the contribution of induced charge and actual collection charge. And here you can see that it reduced the resolution and also leakage of those events from the full absorption peak right in the region of interest where we search for neutrinos double beta decay. So that's already immediate improvement to the physics reach because you reduce the contamination of region of interest. Now that of course is Monte Carlo. As I promised you, we wanted to validate it on data. So here I show you the comparison of resolution between the standard reconstruction and the deep learning reconstruction on all of the calibration Turing data that we had. So not just a particular cherry-picked run, but all several years of data taking. And here the blue is the resolution obtained with deep neural network for that particular run, and red is this traditional reconstruction. You can see that across the board, you have an improvement from 2 to 6%, with maybe just a few outliers, which is just 5 data sets out of several years. We didn't really bother some pathological cases. We didn't really worry about them. And another interesting point here. So after we understood and demonstrated that this improvement comes from this traditional recon, those gray boxes, not doing a well enough job at reconstructing those mixed induction and collection signals, that actually led to the traditional reconstruction improvements. So here we go, speaking about deep learning being a black box that is hard to understand. Here on the opposite, it fed back into our traditional reconstruction and says, hey guys, that's what we need to do and improve. And we went ahead and did it and tried to add this another box to this traditional recon. And it did get better, the traditional recon, but it still didn't reach the ultimate performance of the convolutional neural network. So another application is reconstructing the position of light. So here we use the completely data-driven training. So as I said, we have 2 information channels, and with charge wires, it's very easy to reconstruct the position. Basically, it hits this wire, so you know where this wire is positioned, right? But reconstruct the position using light information is much harder. So we use then the charge reconstructed position as the truth, and we use it to train another convolutional network to understand those patterns of light hits on different IPDs. And here we could not even compare with traditional recon because we didn't have a traditional reconstruction of light position. And we got performance and did well. We validated it by different ways, by looking at different types of calibration data or physics data cut in different parts of the detector to make sure that we can reconstruct with that accuracy actual data events of different topologies. And this is advantages because there are some events where you actually lose charge and you can't use that more sensitive information channel. So having validated your network, you can then apply it and use. After that, we switch gears and we start doing physics because ultimately we just physicists, right? We're interested in deep learning just as another tool to help us do physics. So our ultimate goal as physicists is to recognize those and search for those neutrinos double beta decay events and distinguish them from background. So our third application was to actually construct a signal background discriminator based on deep neural network. And we did it to an extent, right? We build a discriminator that tells you the likelihood of that event being a beta type event or gamma-like event. And then we added the output of that discriminator with the other high-level futures developed using traditional reconstruction, and in the end constructed this kind of traditional likelihood function and performed the, again, traditional likelihood analysis. But nevertheless, using this additional output of the discriminator as one of the observables allows us to improve the overall sensitivity of experiment. And this is not a technical publication like our first deep learning paper. This is actual parallel paper where it went to, and so it worked mostly by the grad student of our deep learning group. And with 5 minutes.
Sorry, Igor. Yeah, it's been 15 minutes. I think 5 more minutes dedicated for question. So maybe a bit less than 5 minutes.
Less than 5 minutes, right?
Yes, I think including question next 4 minutes.
Okay, just to finish up, there will be more slides on the more interesting stuff that is coming out from more recent work. I also had some other more recent work that I want to talk about that we don't have a speaker today, but I can finish and maybe talk about that later, or maybe there will be question. Do you want me to show the Slido page, Kazu?
That would be great if you have a link. Do you have a link?
I believe so, yes. So I will show you both. Yeah. So let me bring you to the summary. So how did you determine what information the machine learning was picking up on the traditional recon was missing? So, right, one of the things that we did is we had an idea that reconstructing induction is hard. So we went ahead and we created separate Monte Carlo samples with the induction turned off. And we saw what's going to happen to both traditional recon and to the Monte Carlo, and to the deep learning recon trained on this Monte Carlo. And when you remove the induction, you see that the performance of deep learning networks approaches the performance of traditional reconstruction. So that tells us there is something in the kind of smoking gun. There is something in the induction physics that is being disentangled by deep learning. And there was another plot that I don't think I have in my bonus slides that also allowed us to kind of pinpoint it even further, to correlate the events caused energy we reconstruct better than in traditional way to the amount of induction that we add in the Monte Carlo. And we also, by the way, we also saw that induction signals is something that we do much better if we want to reconstruct the position. That's something I didn't have a chance to cover here. We also can reconstruct the charge position much better. Again, because we can use this induction signal. And this is one of the ways that we show here, that if we plot the residuals of position reconstruction as a function of the induction signals, we see that deep neural network effectively has a way of calibrating it away, while the traditional reconstruction just doesn't pick it up.
Igor.
Yep.
Thank you very much for the answer. Would you like to just finish up your slides, because I think we do have a bit more time towards the end of this session.
Oh,
you have this position. You have this position reconstruction. I think it's something that discussion group discussed yesterday. So I thought maybe some people are interested in.
Yeah.
Sorry, I didn't mean to really cut off your slides. So if you could kind of quickly finish them, that'd be great.
Sure. So there was some of the stuff that's not yet published, so it's preliminary, and yeah, I guess don't copy it out. But more recent work is we wanted to reconstruct the charge position and see if we by chance can do better there as well. So this is the network that we use. In fact, it's effectively four convolutional networks that like four eyes that look separately into wires in one part of the TPC and another part of the TPC. Right, but because the signals there should be physically equivalent, we actually then concatenate those signals, and we share the weights so we don't unnecessarily increase the complexity of our network. So after we start reconstructing the Monte Carlo events, the position using deep neural network, we saw like a drastic improvement compared to our traditional reconstruction. And you would think, why is it? Shouldn't be hard to reconstruct position, and we didn't expect that we can get a substantial improvement. So haven't seen previously that if you're not careful, your network can learn to cut corners and do them physically good reconstruction. We were, of course, very skeptical on first, and we started doing these checks and tried to understand what is actually the ultimate position reconstruction that you can extract. That's something that was discussed yesterday a little bit at the discussion session as well. And one way to ask for that is to actually try and do some simple, let me show it, some simple Monte Carlo studies. So starting from like a simple theoretical limit that if you had a point-like source and you have the wires positioned with a certain pitch, then the box distribution gives you the ultimate precision of 2.6 millimeters. But in reality, you actually, your events, the charge clouds, they are distributed and they have a chance to hit more than one wire. So that allows you to do the, like a charge weighting. So you can actually expect performance improvement in your resolution. And then there is an effect of diffusion that actually further expands your cloud so you can improve even better. And here we can actually approach what we see with traditional reconstruction, but deep neural network still was doing better. So that's again when we turned to the to this effect of induction that produces that very small signals on neighboring wires that further allows you to kind of improve this effective charge weighting, so to speak, and take this additional information. And that explained it. So using this validation, we convince ourselves that that improvement is actually real. And this is an improvement of basically a factor of 2 or more. However, I should tell you, this is only on the single site events. So before we kind of release it to a wider community, we want to also learn to reconstruct multi-site events, and that is more challenging. So we're still working on that. And yeah, but that basically the last applications that I wanted to say, and then following talks.
Thank you very much for your talk, Igor. I think that was wonderful, and I'm glad that we went over the unpublished part, always the exciting parts of the workshop. Okay, thank you. So I think we're gonna have a follow-up more in the recent and exciting topics from EXO. So first one is Seth. Are you out there?
Yeah, I'm here. I think, let's see. That seems to work.
Wonderful. Would you like to take away?
Sure. All right. So as Igor had in his slides and mentioned, I am one of the graduate students working on EXO-200. I am at University of Massachusetts Amherst, and the focus of my work is moving towards a deep neural network analysis of xenon 137 decays to cesium 137 in EXO-200. So the EXO-200 TPC is a xenon TPC, and it has an isotope ratio of 80.6% xenon 136 and 19.1% xenon 134, with the rest of those percentages being xenon impurities. Xenon 137 is not stable, and so it is not present in those impurities. It has a half-life of about 3.8 minutes, and so it decays very rapidly. And so on the course of the lifetime of the experiment, it's just essentially not present in the cell. It can, however, be created in the cell from cosmic neutron flux, but this only occurs at a rate of 400 events per year. So if you want a good number of xenon 137 events, you need to breed them in the cell using a neutron source. And in our case, we used an americium beryllium source. So this americium beryllium source was used in a calibration campaign towards the end of the EXO-200 detector lifetime. And the way it worked was you would insert the ambi source into the S5 position on the detector, which was basically in the middle of both TPCs. You would allow it to activate a lot of species inside of the detector, and then you would retract it out of the calibration spot and allow your data to enter what was called a decay phase. And so what you wait for is you wait for the activity in the cell to die down till you have an activity of about 1.3 events per second. And then you begin taking data over that time of low activity. And in there, you should find your xenon 137 data. So the xenon 137 decay, has a high branching ratio of 67% into the ground state, but 31% of the time it will decay into the first excited state of cesium-137. Now, this decay is accompanied by a 455 keV gamma ray, which has a half-life that's so small it is essentially simultaneous with the initial beta decay. Now, as Igor mentioned, with gamma ray events being multi-scatter events inside of a detector, this means that decays to the first excited state of cesium will be predominantly multi-site events, while decays to the ground state will be primarily single-site events. Now, when these decays happen, they are imaged on the waveforms and they're recorded on the 152 channels for charge data. And this analysis primarily uses only charge data. I have not looked at light data, but that is being talked about later on with Shaolei's talk. And the window of waveforms that this information is captured in is about 2048 microseconds, cut down a little bit to make training on the DNN earlier. We cut a little bit off of each end to capture mostly where the signal is and just chop out a lot of the noise. So an analysis to the decay of the ground state of cesium-37 has already been done. The results were published this year, and it succeeded in measuring spectrum of the beta to the ground state. This study is seeking to complement the former by measuring the spectral shape of the excited state decay. Now, the reason we want to do this is because the ground state decay from theory does not have any dependence on axial vector coupling, whereas the first excited state does have a dependence on these axial vector coupling. And so if we measure both of these beta spectrums, we can compare the shapes, and it should lead to a measurement of any quenching effects present in xenon-137. So going back to this idea of using the waveforms as an image, you can think of using a convolutional neural network to explore this image, especially because the difference between a ground state and excited state decay is primarily seen in the topology of these events. The convolutional neural network should be able to extract the features from the shapes and the distributions of these multi-site waveforms and hopefully be able to tell the difference between them. And we've already demonstrated, as Igor mentioned, that these convolutional neural networks can learn from our waveforms and be competitive with traditional analysis methods. So the training data used is Monte Carlo simulated, and we generate waveforms with truth values that can be attached on. Now, these events, once they're Monte Carlo simulated, they can be prepared into a binary file format to train the neural network. And it's not just signal we simulate, we actually tag noise onto our simulation waveforms that we measured in real data. And so these simulated waveforms are a combination of what the simulation says the signal will be and what the noise should be from what we've already measured inside of the detector. Because we're using this Monte Carlo simulation, it does allow for very controlled studies on what types of signals impact the performance of the DNN. So because we're using this Monte Carlo, we can actually get very, very precise about what is going on inside of an event when we simulate it. For example, the waveform I've shown, when I made this plot, I also pulled the information and I was able to figure out exactly which peak corresponded to exactly what signal from the decay. I pulled a multi-site event, and the large peak is from a high energy beta, and the two smaller peaks that are shown are a combination of the energy that was deposited by the 455 keV gamma ray. And this ability to know exactly what is causing what signals is very powerful for training these neural networks. So the current network that I have designed is, it uses primarily convolution and pooling layers in order to do feature extractions. It uses an L2 regularization. Currently, I use it at about 10 to the minus 2. Depending on how things progress, that can change. The network is trained at Slack on their GPU clusters to get a very accelerated training rate. And it is programmed using Python with TensorFlow and Keras packages. So a benchmark for how this DNN performs is how well does it do when you feed it a very clean event. Now, clean is up to debate about what you would consider clean, but the way I'm defining it is it has to happen inside of a fiducial volume cut, which in EXO-200 is a hexagon that has an apothem of 162 millimeters. And if the event is an excited state, I required it to have at least 93% of the gamma ray energy captured in the simulated wire signal. This 93% is not really rooted in any specific physics. It's just an arbitrary choice that's a starting point. But using those criteria, the network shows very good performance on what should be a very easy data set for it to work with. Even after 45 epochs on 12,000 events, the loss was continuing to decrease at an exponential rate, whereas the accuracy had early on plateaued and stayed very close to perfect accuracy for the whole training. Now, where is it at on, unclean data, unfiltered data? So the preliminary results on that are promising, but they're still in very early stages. So if you don't put any restrictions on the gamma ray energy deposited on the wire signals, you do see an accuracy that rises quickly and then plateaus of around 85, 86%. But the loss plateaus as well very quickly. Now, these plateaus are still poorly understood why it's happening, and the hope is that by looking at these more clean events, insight into what the DNN is learning to do in this data set can be shown by slowly introducing these complexities. So really, I'm wanting more data to work with and simulate. And these simulations do take time, so I'm constantly adding to my data set to make sure that any inaccuracies or losses in the network are not being caused by just not enough data to learn from. And because we can run on Monte Carlo simulation, getting access to this new data is very, very easy. It just takes time to run the simulations. That 93% energy threshold is an arbitrary choice for the gamma ray, and it does need to be relaxed over time to include more gamma escape events. When you move to reality, gamma rays, they can just completely escape the detector without depositing any energy. And so that will definitely have an impact on the signal, because the neural network is depending on that gamma ray likely to just tell the difference between a ground state and excited state decay. Also, backgrounds need to be introduced. Now, the backgrounds are, for the most part, we have a good understanding and grasp of what our multi-site backgrounds are, but these need to be introduced into the training set so the network can learn to tell the difference between the backgrounds and the signals. All of this being said, the convolutional neural network does show promise for identification of decay modes in EXO-200, and hopefully this work will continue to progress very well. That is all I have, and so I can take questions now.
Okay, thank you very much. So I think there is one question. Do you always have to, do you want me to read it, or do you want to?
Yeah, I'll share it. Can everyone see that?
No, I think you're just sharing the application maybe right now.
Okay,
which is maybe PowerPoint.
Yeah, let me do.
I could share the, or, okay, fantastic. So this way you can also share back to the slides.
Yes. Do you always have to first develop a traditional reconstruction to allow you to apply a fiducial volume cut or other types of data cleaning? So we do have a traditional reconstruction for these. This study is happening in parallel with a more traditional study that Igor is working on, that is using these traditional methods to analyze this data. And so I can use the same cuts as them, but I can also, how do I put this? So I can use the same cuts that they have used, but it also allows me to be more relaxing of the cuts or more stringent, because maybe the DNN has this discrimination power that the traditional analysis will lose out on.
If I may add, so in principle right now we have also a network that can give you position reconstruction, which in principle, if you wanted, you could also use to apply the fiducial cut, right?
Yes.
Okay. So I think that's all questions. So thank you very much for your talk. Thank you very much again. And then let's move on to the next one. And the next one is, of course, again, EXO. No, yes, from Shaolei. So are you there?
Yes, I am.
Fantastic. Would you like to go ahead?
Sure. All right. So I'm also a graduate student working for EXO collaboration, and I will make a short introduction about our studies in training GANs to simulate the EXO-200 scintillation signal. So as Igor has mentioned before, that the EXO-200 has a bunch of APTs on both sides of the time projection chamber to measure the scintillation light. These signals are quite complex, and we currently want to know better about them. So it's definitely to do more simulations, but that's not a very easy job because of the complexity inside the chamber. And we currently don't have a very good way to do that. So that's why we are looking forward to using the generative adversarial network to find a new approach to the fast simulation. So trained with now the real waveform we have, it should be able to just easily generating some artificial waveforms, just like what they did to creating some fake human face. And in addition of that, we would like it to show some dependencies about the positions energies of the events, because we don't want it to be completely random. Then we have this structure of the Wasserstein GAN, and we can see it has 3 separated parties. We have the generator and the discriminator here as like a typical GAN structure, but with additional part called constrainer. This part is trained to supervise the result, and it also make a contribution in the loss function. So it will also it receives the signals from either the constrainer or the data we have, and it gives out the predictions about the positions and energy it have. We would like to minimize the difference between our labels and the constrainers result. So all 3 parts are trained simultaneously as like the GPU clusters. I wrote it in Keras and the TensorFlows. The training set are the events from the EXO-200 calibration sources. To be more precise, I use Vixorium source, so we can see that there's a WGAN peak on the energy spectrum. And also because of the source position is at some fixed point, so their distribution in the space is not very uniform. So I tried my best to flatten those distribution in order to not let the network to cheat from the distribution. Now the training history, if we have a look at the convergences of the constrainer, we can see that both the difference between the position and the energy decreases and approaching to 0. That's good. That's what we expected. So how well are they trained? Let's have here is an example. Now the generator will create the waveform on the left, receiving these parameters on the top. The result, in my opinion, is very optimistic. We can see it already find out some features like the arriving times, and most of the signals are arriving almost simultaneously, and also find out the highest the peak. However, looking carefully, you can see that each channel seems to have a relatively smaller amplitude than the corresponding real one. So this may causing some little bit loss of accuracy. Now let's look at more events. I pick up the events around the WGAN peak, where we use it to creating a light map for calibration the result, calibrate the result. Now, so for both, so find out the peak and add up all the channels of one plan and see how they change along the z-axis. I think it follows a good. The result is pretty good because it already shows on the same, almost the same dependencies for both the plans. That means that we can look forward to using all those maybe in the future events to creating a better light map, so that may give us a better resolutions. Now, looking for a larger range, we can see some parts are not that good. Now here on the graph on the left is the result comparing the constrainers reconstruction result and the conventional EXO-200 result. So it definitely at the lower energy range, it starts to lose in the accuracies. That's probably because of the things we looked at the previous slides, because the amplitude is relatively low at some channels. And on the right side, this shows the reconstruction result of the constrainer, but receives both the real ones, real waveform, and the artificial ones from the generator. And we can see this result that the energy part agrees much better, even though some of the positions reconstruction is not that good. No. So let's focus on the peaks range again and see how the deviations are, and comparing with the three spectrums, and you can see that so it shows in my opinion, a quite good accuracies, but it would be much better if we can have better precisions. So that's the things we would like to do, improve in the futures. Now here's an example using more general events from outside of the training set and the validation sets, and also calculate the resolutions at the peaks. As we can see that although the GANs reconstructed result is not as good as the typical ones, but the difference between the reconstruction result using the real waveforms and the conventional ones are greater than the difference between the reconstruction result from both from the GAN waveform and the real waveforms. So in the next step, I believe that a better constrainer could play a key character in our studies. So far, I think I have already shown that GAN is able to generate waveforms that very close to real ones. Now we would like to do a better job, a better result, and I believe that the constrainer could be improved so that we can reach a better result. Now, in order to do that, I'm recently considering that probably we can change the shape of the input, because right now they are given following this order. That's we label those channels, but maybe it would be more reasonable to give them following their their pattern arranged in the real world. Thank you for your time.
Thank you very much. Okay, so we have like 5 minutes for questions. Let's see. Shaolei, do you have a link? Okay, I can maybe share. Do you have a link? Actually, you know what? Sorry. Yeah, so I can maybe share the question unless you have the question. Do you have a question? Maybe not, right? Let me see. There you go. Okay, so there are 2 questions, although maybe one of them might need a bit more information. Would you like to answer those questions? Can you see the question?
What do you mean by network cheating? Oh, that's the
yeah. So, okay.
Oh, so that's the thing when if you only have the events at certain range, it may then you extend using this data outside this ones, it may losing this accuracies. Especially if you see that it works better at the peak, but at the lower energy part, it is not very good. I think that's something Igor mentioned when I start to train this. How much does this method rely on the reconstruction result of the real simple being accurate? So our results are from the charge ones, which is much better than the scintillation signal reconstructions. Actually, the currently reconstruction of scintillation light is quite bad. I think it's much better, worse than the charge part. So I think this may make sure that the network should learn in a good direction.
If I may add, Shaolei, I think you are correct in what you said, but I still think it's a very good point because we never studied whether we still acquire some bias due to maybe better but still imperfect charge reconstruction accuracy that we use currently at truth labels. So I think we should understand better if it's still limiting us.
I agree with that.
Okay, thank you very much. Thanks again for the talk and also addressing these questions. Yeah, so all of you guys, Igor and Seth and Shaolei for the team of the EXO researchers. So I think we reached in 10:30, which is the target time for ending this second session. And I think we have finished all the talks. I believe what the schedule is after half an hour break, we will have 2 breakout sessions. One is quantifying uncertainties in inference, and the other is ensuring robustness of systematics. Scott, do you have any comments to add, or is it okay to break and ask people to join either of these rooms that you're interested in?
Yeah, thank you. And I'll just, in case it's unclear for people, because the 2 topics may sound pretty similar, I guess the quantifying uncertainties, as I mentioned in the email, is things like, for example, a Bayesian network or likelihood methods to figure out, you know, how do you make this final estimation of what your uncertainty is, so you can get a 90% confidence level limit or the significance of a signal. Whereas ensuring robustness to systematics is closer to, for example, what Corey was presenting, where we're trying to understand how do we make the network in the first place designed to minimize those final uncertainties. And in particular, systematics related to differences between data and Monte Carlo if you're using Monte Carlo for the training. But yeah, you're right, Kazu. We have a 30-minute break now, and then please join whichever of those two rooms you're most interested in.